Hello everyone, my name is Harish. I'm here to present our experience in building and deploying a practical and scalable federated analytics stack at Meta. All right, first let's start with what is federated analytics. It's a distributed computing paradigm designed to answer analytical queries and derive insights from data that's held locally on users' devices, right? All under the coordination of a central server or service provider. Okay, why do we care about this particular problem? So, increasingly, we see more data that is being generated at the edge device, right? And these are also the types of edge devices are also increasing, right? Like from mobile phones to like sensors to smart glasses, watches. Like we are just seeing more and more of data being generated at the edge device. So now the question is, can the data remain at the edge? There are many reasons why one would want this, but the primary one being privacy. This leads us to the next part, like which is how do we improve products when data is present only at the edge device, right? This is where federated analytics kind of come in. We move compute to where kind of the data is, right? We have the data that is there on the device, and then we run the computations on the device and derive minimal focused information that is sent over to the downstream users, right? Only aggregated information gets sent to the downstream users of the platform. One can think of FA as a map-reduced job, right? Like where the map happens on the edge device with the private data, and the reduce happens on the server. There are many challenges when deploying this and when using this in practice. We are not the only ones solving this problem. Various FA systems have been described both in the industry and academia. However, many of these systems have restrictions that tend to limit their wider applicability as a platform, right? Like some of these, for instance, is analysts lack the flexibility that they need to obtain the necessary information. And then there is no support for ad hoc queries, right? Like it requires analysts to consider a priori all of the queries that they need to be answered weeks in advance. There is scaling limitations, and this is across multiple dimensions, like where we want to scale the number of clients that participate in a single query. We want to scale the number of queries that a single client can compute. To add to this, we have clients are heavily resource constrained and can participate or drop out at any point in time. And one other limitation that we encounter is the privacy management becomes quite complex, right? Like there are multiple actors here with varying trust levels, and there is the device, there is the server, there is the analyst who is requesting the computation. So all of this leads to hard to reason and manage privacy here. So slightly digressing, federated analytics is built alongside another popular technique called federated learning. In fact, we developed and published an FL system under the same name, PAPAYA, a few years back. Conceptually, these are very similar, right? You run some computation on the device with locally held data, right? With federated learning, you are running a machine learning training algorithm, and then you aggregate model weights on the server. In federated analytics, you run analytical computations and aggregate reports, right? So they are conceptually very similar, but differ significantly in the workloads. For federated learning, you only require a very small subset of users, who run a very compute-intensive job on the device, and the message size that is being uploaded is in the order of megabytes, right? You are essentially uploading the entire model back to the server. Versus with federated analytics, you require a much larger set of population. In fact, all of the devices need to report back. The computation is very lightweight, and the message size is also small. Right? There are these differences led us to develop a new system and a protocol for federated analytics. So before we head to the design and its evaluation, it's useful to talk about an important building block that we use. No matter what approach we use for federated analytics, it requires client devices to send some information about their data. In order to provide robust security and privacy guarantees, it's necessary to rely on some form of secure computation. We rely on trusted execution environments. So you can think of trusted execution environment or TEs. They provide a secure and isolated environment for processing data without leaking any information to an external observer. These are backed by hardware guarantees. And through a process called remote attestation, it provides a way for clients or like third parties to verify that they are in fact speaking to a TE that is running a particular measurement or code. All right, let's moving on to the design. So broadly speaking, there are two categories of FA. There is cross silo and cross device FA. Cross silo is where there are few entities and each have a large data set. Think of organizations or companies collaboratively solving a problem without revealing their individual data points. And then there is cross device, which is like think of mobile phones or other edge devices where you have a much larger number of entities, each with a very small data set. So cross device setting is our focus for the design, and that's what we have optimized for. So there are three main components when it comes to Federated Analytics. Like we have the client runtime, which is responsible for executing the client protocol. We have a secure aggregator that is hosted on TEs that is aggregating all of the client reports. And we have an orchestrating server that is responsible for the entire end-to-end process. So a typical FA workflow consists of multiple steps. Right, like it starts with the query creation, where the analyst define the query that they want and register it to the system, and then the client will poll the server and then download the query spec, transform its local data from its store, and then send this computed information to the trusted secure aggregator for aggregating across, which aggregates across all of the different kind of devices. Finally, this aggregated report gets sent to a trusted this aggregated report gets sent to the orchestrator for doing more post-processing and publishes the result for consumption. And this is the same kind of setup. Like this is the overall system describing the same steps from the previous slide. It all starts with the analyst defining kind of the query that they are interested in. It maps to something called a metric config, which gets broadcasted to all of the different clients who do the computation, forward it to the trusted aggregator, and then which forwards it to the which aggregates and forwards it to the untrusted orchestrator, which post-processes and produces the result that is consumed by the analyst. All right, diving into how the actual query looks like and that the analyst needs to author. So it's let's assume the data is already present on the client, and then like the analyst is now defining the query. So the query is actually broken down into multiple bits. Like first is what is the actual query of interest, right? Which itself is in two parts. What is a local computation that needs to run on the actual device? This is defined in a free-form SQL. We chose SQL because it's easier for analysts to work with and define their query in this particular fashion. And then the next part of the query is how do you aggregate it across devices, right? Like what is the group by column, like how are you kind of aggregating it across devices? Then once you define this query, like there are two more kind of components. We ask what is the privacy requirement for this particular use case. So not all use cases are equal. So some may require a more stringent policy, some might require a more relaxed one. So you need to define what's relevant for the use case. And finally, we ask where the result needs to be published. So like on the right, you see how the query, a typical query would look like. So one key observation when we were trying to do this, like define the query is with custom transformations, like with SQL queries or like other forms of custom transformations on the device, a very small subset, a very small set of aggregation primitives are sufficient to support a wide range of queries. So now deep diving onto the client runtime. So the client runtime itself comprises of several subcomponents from engine to like store to follow the protocol. Please refer to the paper for a detailed explanation here. I wanted to highlight one important aspect that enables analysts to define ad hoc queries while still upholding the privacy expectations. This is mainly because of the hard-coded privacy guardrails over here. So these are defined by the application owner or the client and are hard-coded onto the app. So these can be like how many queries one can answer, what is the maximum differential privacy parameters, what are the trusted kind of binary measurements, are there data sets that should be off limit for queries, like whatever expectations that you have for the data, like these are all hard coded and hard coded onto the app. This ensures even if there are malicious queries that are being authored and like sent over to the client, they will be rejected by the client. The client gets the metric config, it gets all of the parameters that are used by Ts, and then will independently evaluate whether it can participate in a particular metric or not, and then reject and abort the protocol if the hard-coded guardrails are not met for that particular query. Now getting to the trusted secure aggregator part. So here, the role of the trusted aggregator is only one, right? Its role is to securely sum all of the client reports. Each client sends a sparse histogram. This aggregates all of this sparse histogram and then removes values below a threshold. So we observed that all of the common aggregation types, sum, count, mean, quantiles, etc., can all be built through a pre and post processing of sums. So relying on a single primitive allows the code to be simple, easy to optimize, and reason about privacy. All right, getting to the actual privacy and security of the system. So let's talk about how the data is handled. First, the data at rest is on the respective client's devices, right? This in itself is a big step compared to trusting some other entity to be a steward of the data. The user's device owns and controls the data. All of the user's data is either processed on their device or in an environment where the device can verify how the data can be handled. The clients have full control over the computations. What computations are run, when to run them are all determined by the client independently. And finally, the clients validate how the data will be handled by downstream entities before sharing to them. So moving on to the privacy. We don't need to care about the data that is there on the device or how it's handled on the trusted aggregator. Our focus is about what is observable or sent to the orchestrator, which is the untrusted component here. So for that, we aim to provide strong guarantees. Any data that is seen by the orchestrator is anonymized according to the guardrails or expectations set by the client. There are various ways one can achieve it. Essentially, this boils down to adding differentially private noise, like where you add noise to ensure there is no information about any individual client is revealed. Again, this noise can be added like either all on the trusted secure aggregator or on the client, or you can use a hybrid approach. As a platform, we try to support all of these forms. The only constraint is that the output from the TSA needs to have a certain amount of noise that is added. Going back to the set of challenges once again. So with using a familiar SQL query to define the query, to define the queries of interest and enabling ad hoc query support, the stack we believe is more accessible to analysts. For scaling, we built a robust one-shot algorithms built on a single scalable primitive. We use batched computations on the device to enable us to amortize the cost of setup and server communication. The client initiates the protocol, polls the server periodically, fetches the list of metrics, figures out what metrics it needs to participate in, executes them all in one shot, and shares the result back to the server. And finally, we have predictable load on the server. We will get to this in the evaluation section. And finally, for privacy management, we put the client at the front and center of it. Each client is responsible for their data and set expectations for the privacy of the output. Getting to the evaluation of the system, we carefully chose metrics that represent system and data heterogeneity that we observe in a production setting. So for this, we chose round trip times and request volumes. Round trip times represent a form of system heterogeneity as devices have varying network capability, and we chose request volume as a good proxy for application usage, right? Like more usage means they represent a power user, like who has more data. The queries that the system answered, like for this evaluation, is like we tried to capture the federated histogram of the RTT distribution and the histogram of the request volume, the number of requests per client. The query itself doesn't matter. As a first order approximation, as a stack is query agnostic for the most part. And we evaluate, as one would evaluate any analytic platform here. Once you define your query, how long does it take for the system to iterate over all devices and get the data, like how accurate the answer is, we know the ground truth, and like we can measure it, and what is the impact of adding a differentially private noise. So we look at the collection speed or coverage over here. Coverage is essentially the number of data points processed by the task divided by the total number of data points, ground truth data points in the database, essentially the percentage of data iterated over. As we can see, like within 24 hours, 90% of the data has already, devices have already responded, and like we don't see any bias in terms of the time of day we start the query or in terms of round trip times. The behavior is most strongly influenced by our choice of system parameters with how often the clients check into the server at random. And like looking at accuracy, like we see again, like if you wait for a few hours, accuracy is like pretty negligible when you compare it to the ground truth. And the impact on privacy noise, impact because of privacy noise, like to anyone familiar with differential privacy, this should look very obvious, like which is what we also observe is that central differential privacy is very close to providing the same accurate results that one would expect, but like in all, like everything has very low accuracy, as in very low impact on accuracy, and satisfies whatever privacy threshold that one needs to set. Yeah, like yeah, we just wanted to share our deployment that demonstrates it is possible to achieve federated data collection at scale while also making it more practical and like easy to use. All right, thanks.